All right, guys, we're going to talk about solar radiation and the Earth's seasons. This covers one learning objective. The learning objective is solar radiation and Earth seasons, the enduring understanding. Most of the Earth's atmospheric processes are driven by input from energy from the sun. So energy from the sun is a huge part of this course and will be the ultimate source of energy for most of the processes that we're going to talk about. The learning objective, just be able to explain how the sun's energy affects the Earth's surface. So right here, how the sun's energy affects the Earth's surface. Okay, and then we'll talk about the essential knowledge at the end of this PowerPoint. So the vocab, you can pause this now and jot this down. There's not much, but you can copy it down. All right, so weather and climate. I'm just going to bring all of these up. So weather and climate. Weather is day-to-day atmospheric conditions, so it's the temperature, the precipitation, the wind direction, and speed. What's going on in the air that day? That is weather. So we can look at the weather today. I'm looking out the window right now, and it is sunny and about 72 degrees Fahrenheit. That's the weather. Climate, though, that's the average weather of a region over many years. That could be decades, that could be even millennia. So we could talk about the average climate of an entire geologic period, or we can talk about the average climate of Denver in the past 100 or 200 years or 1,000 years. The key difference here, weather is going to change day to day, while climate is the average of those weather fluctuations. So a couple general trends in climate. First off, this should come as no surprise to anybody, but as you get closer to the equator, temperatures are going to increase. As you get closer to the poles, temperatures are going to decrease. Okay, it's going to get colder as you get further north or south from the equator. Temperate regions are going to experience 4 seasons in general. So we're going to have, spring, summer, autumn, and winter. Whereas the tropics tend to experience just 2 seasons, and those tend to be the wet season and the dry season. So what is going to cause the seasons? The seasons are really are due to the Earth's tilt. So what this slide is talking about is its orbit, but the Earth is going to travel around an elliptical orbit around the sun. That elliptical orbit is a very, very slight ellipse. So if I was to draw a really, really poor ellipse, the diagram down at the bottom shows it a little bit better. But right here, we have the Earth where it is a little bit further from the sun, whereas over here, we have the Earth where it is a little bit closer to the sun. Okay, so a little bit further, a little bit closer. The Earth's elliptical orbit really is not enough to contribute to the seasons, though. In fact, the Earth is furthest from the sun on what we would consider in the northern hemisphere the middle of summer, July 4th. Okay, the Earth is actually closest to the sun on January 3rd, what we in the northern hemisphere experience as winter. So this elliptical orbit doesn't really do much at all in determining the seasons. And in fact, you'll notice that the difference in the closest and furthest point from the sun is only about 3.2%. Okay, so it's a really, really almost negligible distance. It does affect a little bit, but not enough to cause our seasons. What the Earth's seasons are caused by is its tilt. Okay, so the tilt of the Earth is at about a 23.5 degree tilt from what would be perpendicular according to the plane of its orbit. So the plane of elliptic is the plane that it orbits around the sun, and the Earth spins on its axis, the axis of rotation, not straight up and down perpendicular to that at a 90-degree angle, but at a 23.5 degree angle. And this angle has changed a little bit over time and continues to change. That's what we call wobble. But right now it's at 23.5, and that's not going to change for, within our lifetimes or within our grandkids' lifetimes. Okay, that tilt is responsible for the seasons. Okay, so there are some important dates with the seasons that you guys do not need to memorize. You do not need to know what day the summer solstice is. You do not need to know what day the winter solstice or the equinoxes are. Okay, so I am going to reference them, but they are not important for you to memorize. So essentially what's going on in these diagrams is that the sun is up in the sky. Obviously this is not to scale, and that is a very poorly drawn sun, but that sun is going to be shining down on the Earth Electromagnetic waves are going to be moving to the Earth, and during the summer solstice, what we experience as summer in the northern hemisphere, the sun is going to be pretty much directly overhead, or it's going to appear to be directly overhead. The reason that it appears to be directly overhead is because the Earth's tilt, again, is at that 23.5 degrees, and that 23.5 degrees is angling one side of the planet closer to the sun. During the summer solstice, that side that's closer to the sun is the northern hemisphere. And in the northern hemisphere, the sun's rays are going to be coming down at a more direct angle, almost 90 degrees to the Earth's surface, which is going to transfer a lot of energy to the Earth's surface, and it's going to be warm in the northern hemisphere, and that's going to be summer. Whereas in the southern hemisphere, these rays are coming in at a very oblique angle. The Earth's surface is angled away from the sun, or at least the tilt of the axis is angled away from the sun, and not a lot of energy is going to be passed on because it's at that oblique angle, and they are going to experience winter in the southern hemisphere. The opposite is going to be true during what we experience as winter in the northern hemisphere during the winter solstice. So you have your sun. That sun again is shining rays down on the Earth, electromagnetic rays, and during the winter solstice, the northern hemisphere is angled away from the sun. Those solar rays are coming in at a very oblique angle and not transferring a lot of energy to the northern hemisphere, and the northern hemisphere is therefore going to be in winter because it's not as hot, whereas it's going to be summer in the southern hemisphere. Okay. The other two dates on here are the equinoxes. Those equinoxes occur when the sun when the Earth's tilt is essentially perpendicular to the sun. Okay, so during the spring and during the fall, there is a point in the Earth's rotation, which I'll show on another slide, where it is essentially perpendicular to the sun. Okay, but the seasons are due to the tilt of the Earth, especially summer and winter. All right. So this is what I was talking about just now about the vernal and autumnal equinoxes. But essentially, with the Earth's path around the sun, the Earth is always going to be pointed in the same position in space relative to the sun. So you'll notice that this axis does not change at all. It's always going to be 23.5, and it's always pointing in this direction. On this slide, it's always pointing in the same direction. Okay, that leads to, again, the seasons where during the summer equinox, we're going to have the northern hemisphere, summer solstice, that's why it sounded weird. Summer solstice, we're going to have the northern hemisphere facing more directly towards the sun due to that 23.5 degree angle. Again, this is further away from the sun, so that doesn't count for the seasons. What counts for the seasons is that angle, 23.5 degrees of the Earth's tilt. So that angle is directly or more directing those solar rays more towards the northern hemisphere, less towards the southern hemisphere. You have summer in the north, winter in the south. As the Earth goes around its orbit and you get the autumnal equinox, that's where it's that tilt is essentially perpendicular to the sun. Okay, so that tilt is still going in that angle, but it is neither pointing towards nor away from the sun. So day length in the northern hemisphere and the southern hemisphere is exactly the same, and you get that transition between summer going towards winter. Okay. So this is essentially showing the same thing. The Earth's orbit and then the tilt are pointing in a different direction because it's at a different. It's looking at it from a different position in space. That's okay. But you notice that the tilt is constant, always pointing in this direction. If I can draw straight, which I can't with my mouse, always pointing in that direction relative to the sun in space. Okay. So because the sun is the main source of the main source of energy for the surface of the planet, there is another source of energy in the planet's core, which heats up, the core, the inner, the outer, as well as the mantle, and that drives plate tectonics. But that is really all that it drives, along with some geothermal stuff like energy, like we'll talk about, volcanism. The rest of the energy on the planet comes from the sun. So it's the main source of Earth's energy. All the heat, all the light, all the primary productivity, so all the photosynthesis that's happening on the surface of the Earth is due to the sun. So extremely important. Um, and that's why we have, again, in the northern hemisphere, which this diagram is showing, northern hemisphere summer, we have all that primary production, all that photosynthesis happening in the northern hemisphere because the solar radiation is giving it longer day length and it's more directly overhead, or at least appears directly overhead from the surface of the Earth. Insolation, this is a term referring to the exposure to the sun's rays. So the technical term is the rate of delivery of direct solar radiation per unit surface area. We can look at that as meters squared, kilometers squared, whatever unit of surface area we want to look at. Okay, and as you go further up in latitude, so as you go higher into latitude, both north and south, insolation is going to really depend on what season you're talking about, whether it's summer or winter. But the average is always going to be higher at the equator because the equator is going to get around 66.5 degrees of sunlight relative tilt, relative position of the sun and the sky. It's going to get sunlight all year round. Okay, whether you're talking about one of the solstices, whether you're talking about an equinox, the equator is always going to get lots of sun, which is why it has the highest rates of primary productivity on the planet, like when tropical rainforests. Okay, but seasonally, the latitude that's going to experience the greatest insolation is going to be whichever hemisphere is pointing towards the sun um, and is experiencing summer. So in the northern hemisphere, that'd be the summer solstice on July 4th. Okay, one thing that I really want to hammer home is just expressed here. So summer in the northern hemisphere is always going to be winter in the southern hemisphere, again, due to the tilt of the Earth. I can't stress how many times I'm going to say that. But summer is going to be, northern hemisphere summer is going to be winter in the southern hemisphere. Winter in the northern hemisphere is going to be summer in the southern hemisphere. So say that you're a huge skiing fan, you could, in theory, ski all winter in the northern hemisphere. And then once the ski season is ending, you fly down to New Zealand or Patagonia and you ski for another 6 months. And then you fly up to the northern hemisphere and you experience winter year round because you'd be going from winter in the southern hemisphere to winter in the northern hemisphere um, and cheating the system by flying. Okay, so this correlates with daylight hours. I mentioned daylight hours a few times. This is due to the tilt of the Earth. Summers are going to experience longer days. They're getting more solar radiation, and they're getting more energy from that, which is leading to all the photosynthesis happening during the summer. What's really interesting, though, is what happens in the Arctic and Antarctic. So if you look right up here at the North Pole, you'll notice that the North Pole is facing towards the sun. It's at a relatively oblique angle, relatively shallow angle, but it's going to experience sunlight 24 hours a day if it's above 66.5 degrees, 66.5 degrees north. So it's going to experience 24 hours of sunlight a day at the summer solstice. Okay, if you're right at the North Pole, it'll be for maybe a month bookending the summer solstice. Okay, until you get to the equinox, and then it's going to flip. So in the northern hemisphere, during winter, you're going to have 24 hours of darkness. And then obviously it's going to flip on the southern hemisphere as well. Okay, so revisiting these learning objectives, this is topic 4.7, solar radiation, Earth seasons. Most of Earth's atmospheric processes are driven by input of energy from the sun. We didn't talk a lot about those, just weather and climate very briefly, but we will continue talking about those in the next couple lectures. Okay, learning objective was explain how the sun's energy affects the Earth's climate. So explain how the sun's energy affects the Earth's climate. We talked about insolation, and we talked about how the Earth's main source of energy is that sun, and it's dependent on the season and the latitude. And again, that's all due to the angle of, or the tilt of the Earth, which is what, wherever it was in the learning objectives, down here at the bottom, so the tilt of the Earth. We talked about the angle of the sun's rays determining the intensity of solar radiation. So whether the sun is at an oblique angle or whether the sun is at a direct angle is going to determine the intensity of that solar radiation. If you have the sun at a 90-degree angle relative to the surface of the Earth, say at 23.5 degrees north at the summer solstice, the sun is going to appear directly overhead. It's going to be the hottest day, on average, the hottest day of the year because it's getting the most solar radiation. Okay. And then if it's at a very shallow angle, then it's going to be very, very cold year round, even if it's gained 24 hours of sun, just like the North Pole. Okay. The highest average solar radiation, the highest average insolation is going to be at the equator because it always gets, at minimum a 66 and a half degree angle relative to like relative position of the sun in the sky. So it's always going to have a lot of solar radiation coming in, even if it's at one of the solstices. Okay. And then the solar radiation received at a location on the Earth's surface varies seasonally, especially in temperate latitudes. Okay, so the summer day is going to have the most solar radiation, going back to, sorry, this one and this one. Okay, and then the winter, the shortest winter day, the winter solstice is going to have the least amount of solar radiation. Okay, well, I hope you guys found this interesting, learned something new, probably a lot of review though, and I'll see you all in class. Bye.